Okay, let's talk about some redox reactions. This is topic 4.9. So let's get going. Okay, so reduction and oxidation reactions is how we get the term redox. So what we're really looking at is the transfer of electrons. So oxidation is the loss of electrons. That's very important to remember. So oxidation is the loss of electrons, and reduction, so this is the gain of electrons. And you can use this acronym. Leo the lion says GER is a fine acronym to use. Personally, I like to use oil rig because I think it's more straightforward. So oxidation is loss and reduction is gain. But Leo the lion says the loss of electrons is oxidation, and he says GER, which is the gain of electrons, is reduction. So an oxidizing agent is the opposite of what is being oxidized. It is the species that is promoting the oxidation. So we know that a species is an oxidizing agent because it gets reduced in a reaction. And similarly, a reducing agent is the opposite of what is being reduced. It is the species that is promoting the reduction. So they are oxidized, which means that they lose electrons, and an oxidizing agent gains electrons. So let's look at this. So chlorine, you see we use half reactions to show oxidizing agents and reducing agents. That's important. That's going to come back, especially when we talk about electrochemistry. When we get into galvanic cells and voltaic cells, we're definitely going to be looking at half reactions a lot more, but it's nice to get introduced to them right now. So H positive in this reaction, in the manganate reaction, represents an acid, and it is present in order to react with any excess oxygen atoms to form water. Oh, I guess we're looking at the fourth equation. Okay. And in general, acids tend to be good oxidizing agents since they tend to gain electrons, which is also the Lewis definition of an acid. So a Lewis acid gains electrons, and a Lewis base loses electrons. And so we'll look at that when we get to reducing agents. So bases tend to be good reducing agents since they tend to give up electrons with this hydroxide, essentially. So let's talk about how we know it's a redox reaction. So this is a formation of potassium chloride, and it can be thought of as two half equations that show electrons being either lost or gained. So we are going to use this to combine two half equations. So we have our full equation here. The 2K plus Cl2 yields 2KCl, or potassium chloride. But we need to cancel out these electrons. So we have two electrons right here with the chloride and only one electron here. So what we can do is multiply this potassium side. We're going to multiply by 2. And so we're going to have 2K yields 2K positive plus 2 electrons. And then for this, we're going to keep the chlorine the same and say Cl2 plus 2 electrons, because there's really 2 chlorines here because it's diatomic, is going to yield our 2Cl negative. And we need to make sure that our electrons are on opposite sides of the equation, and they are. So we have this and this, they cancel out when they're on both sides. So then we have 2K plus Cl2 yields our 2K positive plus 2 Cl negative, which we can combine to our 2KCl because they're ions with the same charge and they have the same subscript. So that's our full equation, and that's how we got to it by canceling out electrons. And we will do this a lot. We're going to multiply one of the equations by 2 or 3, or sometimes we'll multiply by the least common multiple. So one side will get multiplied by 2, some will get multiplied by 3, and we can see what gets oxidized and what gets reduced by using our oxidation numbers. So an oxidation number is the number of electrons that an atom loses or tends to lose when it is involved in a redox reaction. So we can have negative oxidation numbers which would mean that it's actually reduced because it's gaining electrons or becoming more negative, and that's why we use the negative number. So anytime electrons are transferred, it is considered a redox reaction, and if no electrons are transferred, meaning there's no change in oxidation numbers, then it cannot be a redox reaction. So an oxidation number on an uncombined elemental atom is 0. So O2, iron, anytime, so like Cl2, any diatomic, it's still going to be 0 because that's how it's naturally found in nature. And then the sum of the oxidation numbers in a compound is equal to the charge on that compound. So like polyatomic atoms, like our nitrate, NO3, negative, our oxidation numbers will equal a -1 because we have this negative here. And then our polyatomic atoms like nitrate should add up to their charge, and then solo ions will be their charge. So that's like Na positive or manganese 4 positive. Essentially, that's what that means, solo ions. So we have a few rules to use, and then the rest of our oxidation numbers can be found using these rules. So oxygen is always -2 unless it's a peroxide. If it's a peroxide, then it's -1. Hydrogen is always +1 unless it's a hydride, so a metal hydride where hydrogen's acting like the anion, then of course it is -1. And then group 1 elements are always +1, so that's our sodiums, our lithiums, our potassiums. And then group 2 elements are always 2, and that's our berylliums, calciums, things like that. And then fluorine is always -1 because it is super electronegative and just wants 1 electron. And so if we go back up to our NO3, for instance, and we say that it's going to be equal to -1, we need to find nitrogen. That's what we're finding. So we'll have X, and then our oxygen is always -2, and there's 3 of them. So we have -6, essentially, on this side. So we have X minus 6. Minus 6 equals -1. So then X would equal, we're going to add 6 to both sides, and so we're going to have X equals +5. And so we know that the oxidation number on this is a +5. And so that's how we use our oxidation rules. So let's look at the oxidation number of each of the atoms in the following species. So we always treat these individually. So our oxygen always has a -2, and this isn't a peroxide because there's no hydrogen. So this will be a -6 on this side, and we have 1 sulfur. It needs to balance out. Oh, this is a sulfite, so it has a -2 charge. So this is -6 total. There's a sulfite, which has a 2 negative charge. And so we'll do the same thing we just saw. So we'll do X, which is our sulfur, -6 for our oxygen equals -2. We can add 6 to both sides. And so that means sulfur's oxidation number is +4. So we'll assign that there. I'll say +4. Potassium will always have a charge of +1. Or I'm sorry. Oh, this one's a little weird. Well, we know oxygen's always going to be -2, and there's 2 of those, so it'll equal -4. And so then this potassium means this has +4, but I don't really like this example because usually group 1 metals are always +1, but that's fine. I always usually start with the ones we always know, so like our oxygens and our hydrogens usually, and our fluorines before I get to the metal, because that's usually where our oxidation number changes. So we have NH4, which equals +1. So this isn't a peroxide, so we know our hydrogen is going to be +1. So if we have our oxidation number is +1, we have 4 +1, so we have +4. This nitrogen has to equal X. We'll say it's X, and there's only one of them, so it's 1X. and then X equals negative 3, because negative 4 plus 1 is negative 3, so our nitrogen here is negative 3. For here, the strontium tetrafluoride, or strontium fluoride, will have a negative 1 for the fluorine. It's always negative 1 for that one. And so we're going to say this is 0 because it's not a polyatomic. Oops. That's going to be equal to 0. And so we're going to have a negative 4 because we have 4 fluorines, and then we have strontium, or we can say X, that's fine. So then X equals 4 because we add 4 to both sides. And so we have a positive 4 for the strontium. Oh geez. Okay, so CO, Cl6, 3 negative. So this is a polyatomic. We can tell by the brackets and the charge. So we have CO, Cl6, and that will equal negative 3 when all is said and done. Usually, the oxidation number will follow the charge on the periodic table. So if we don't have any rules, we can usually say this will be 6 times negative 1, because chlorine has a charge of negative 1, plus CO, which is cobalt, and then that will equal negative 3. So we have CO plus negative 6 equals negative 3, and then so we add 6 to both sides, and then so Cl equals positive 3, and that adds up to the charge of negative 3. So that will be positive 3 on that one just on CO. So positive 3, and this will be a negative 1. And that's how we determine oxidation numbers. Let me know if you guys need any more practice with this concept.